And our guest today is Rogerio Rosenfeld from IFT-UNESP in São Paulo. Rogerio graduated from USP, and he did his PhD uh, at University of Chicago. And he went, after that, he spent some years as a postdoc at the University of California in Los Angeles, and the Northeastern University and the University of Sao Paulo. And since 95, he's a professor at UNESP in IFT. So he's well known for his work in dark energy and LHC physics, and he is also serving physics in different administrative levels. So he is vice president of the IFT, of the ICTP Cipher in São Paulo. He used to be a director of the IFT in São Paulo and also president of the Brazilian Society of Physics. He's a member of different big projects, in particular the project which is the laboratory, inter-institutional laboratory for e-astronomy. So this is a project for working with big data in astronomy in Brazil. And he's also a member of several experimental collaborations, experimental and theoretical collaborations like Dark Energy Survey and also Vera Rubin Legacy Survey on space and time. So this is a new telescope that is being built in Chile.
Yes.
So it's a great pleasure to have Rogerio here with us, and so he'll talk more about dark matter today.
Yes. So thank you, Dimitri, for having me here. It's a great opportunity to give a talk to you guys. And I'm going to talk about a recent paper that was published this year. You barely see this, no? 2024. Which is on something about ultralight dark matter. So this is going to be a seminar about dark matter, particularly ultralight dark matter. And I hope you don't get scared by the number of topics that I'm covering here, but the idea is that 99% is a review. Okay, 90% is a review, and maybe 10% is something new. So the idea is to be really basic. So I don't want to lose anyone. So please ask questions if I'm saying things that you don't understand, and let's see how it goes. So I'm going to give a brief introduction on the subject of dark matter, then talk about scalar fields in the universe, the simplest model for dark matter, what we call this misalignment mechanism, which I hope you don't know, because if you know, it's going to be boring. And then ultralight dark matter, the case of axions, something that's called the axion quality problem. And then finally, I'm going to talk about dilatons. And dilatons are the main subject, because these are the candidates that we're looking for, that were studied in this paper. And also the quality problem. So we're discussing some models of dilatons and the quality problem for an ultralight dilaton. And finally, what is the consequence of this study for ultralight dilatonic dark matter? Okay, so introduction, as you probably know, cosmology has become a data-driven precision science in the past several decades, maybe 20, 30 years or so. And this is basically due to the development of several instruments that were important in order to get data to analyze the universe. In particular, I'm just drawing some, it's just because I like history of physics. The experiments that study the cosmic microwave background in greater and greater detail. So every 10 years, there was a satellite that did a great job in analyzing the cosmic microwave background, which was discovered in the 60s. So the satellite COBE, the Cosmic Observer Background Explorer, in 1990s, they were the first one to discover, well, first to measure the degree of homogeneity in the background radiation, measure the temperature to incredible precision. So it's the best black body that anyone has ever measured, is the cosmic microwave background. but also they found the fluctuations. So it's not perfectly homogeneous. They found these very tiny fluctuations in the temperature of the cosmic microwave background, 1 part in 10,000. Um, and they got the Nobel Prize, of course, for this, right? The people that were involved in this project. And then WMAP, the Buchelson Microwave and Isotropy Probe, another satellite, 10 years after. So this is roughly. And then finally, the Planck satellite, 10 years after. And Planck is not taking data anymore, so it's about time to have another satellite sometime soon. But they're planning to have a new generation of microwave background experiments on Earth. But then it's interesting I just want to notice that some groups in Brazil were starting to work on this already in the 90s, even before 90s. There were some balloon experiments to measure the cosmic microwave background by the group of Tirso Vilela at INPE in São José dos Campos. And they were also were working on this advanced cosmic microwave instrument, so ACME, Explorer, ACME. And then there are also many other experiments to explore the cosmic microwave background. And the cosmic microwave background is an important source of information about cosmology, dark matter, dark energy, etc. The cosmic microwave background is still the most precise data to study the universe. And just to give you, this is just I was going to tease Farinaldo about this because this work of the group of Tirso, there is still something that is not completely solved. Who works with you work with Farinaldo, right? Farinaldo, it's just for you this, because I'm talking about the work of Tirso Vilela at INPE, and they worked on this experiment called Arcade. So it's a balloon experiment to measure the radio background in the universe, and they found an excess that is not explained until today. So this is something that Farinaldo probably is working on or or has worked on. So this is 2024, and this is an experiment Arcade. You cannot see because the resolution is not so good. But again, this is a excess radio background which was detected by this experiment with a Brazilian participation, Arcade. So this is the cosmic microwave background. Then the other source of cosmological information is the Large Survey of Galaxies. So this is also something that has evolved in time. Maybe one of the revolutionary surveys. The first one was the Sloan Digital Sky Survey, SDSS, which actually took data for 20 years, and they collected 1 million galaxies or spectra of galaxies, and they measured what's called the baryon acoustic oscillations, which is a standard ruler in the universe. They released their last data in 2019, and this project has pretty much stopped, but it was now, there are other projects, and one that I'm involved with is the Dark Energy Survey, which took data from 2012 through 2019 also, and it has data of 300 million galaxies, but it's not spectra. We have the positions of the galaxies and the galaxy shapes, and we measure the redshift using different different images at different wavelengths. And this is what Dimitri referred to, this linea, which is the Laboratório Interinstitucional de Astronomia, which actually gives support to the Brazilian participation in different surveys like DS. Also, some people are working as DSS, and also LSST. And the final results, so the experiment stopped taking data in 2019, and the final results are coming up this year. So it takes a long time to analyze data, believe it or not. It's not simple. So it's a huge group of people, and they have to understand the systematic errors. They have to make all the cosmological analysis, have all the what we call pipelines ready. So it's not simple. It takes a long time. Anyways, the year 6, the final result is coming up this year. And maybe you heard, maybe you have not heard, there's a new instrument that started taking data in 2020, which is called the Dark Energy Spectroscopic Survey, or DESI. Have you heard of DESI? Who has heard of DESI? You have heard of DESI, and you have heard of DESI. Huh? Sorry? DAISY is a laboratory in Germany with an Y. And it's a laboratory where they have a group of theoretical physicists and also experimentalists. They had an accelerator there called HERA. It doesn't exist anymore. And they do X-ray laser. Yes, so not this is totally different. This is an instrument which is in an observatory in Arizona, and is collecting data from galaxies, spectra, uh, very much like this Lone Digital Sky Survey. So this is actually the experiment that succeeded this Lone Digital Sky Survey. And started take data 2 years ago. It's supposed to take data for 5 years. And in 1 year, this is what's really amazing. In 1 year, it has taken as much data as 20 years of Sloan Digital Sky Survey. And I can explain why. Of course, technology advances, but this is truly, truly amazing. So in 1 year, it's like 20 years of Sloan Digital Sky Survey. In fact, Brazil has two principal investigators that are, in principle, could work at the DESI collaboration because of in-kind contribution from Linea. And these are the results of the year one analysis, the analysis of the first year of data of DESI. These are the results on what's called the baryon acoustic oscillations, which I can explain later if you're interested. And finally, there is this Vera Rubin Observatory's Legacy Survey of Space and Time, or LSST. So LSST is for Legacy Survey of Space and Time, which is a project that is going to be conducted in the Vera Rubin Observatory. And this is the telescope. It's called the Simony telescope inside. It's being built as we speak. It's a brand new 8.4 meter telescope with the largest digital camera ever built, 3.2 gigapixels. And actually, the camera is being shipped from the US to Chile. So this is in Chile. This is a mountain called Cerro Pachón in Chile, which is actually the mountain opposite to the Dark Energy Survey. They're all next to each other. And there are more than 100 scientists from Brazil which are engaged in this project, mainly due to Linea efforts. So we plan to build what's called Independent Data Access Center, which will guarantee these positions from Brazil. I'm the current coordinator of the Brazilian participation group in the LSST, and also we have the only INCT in astronomy or astrophysics today, which is this INCT of the universe, which is to give support for these participations. And we're organizing the first LSST at LATAM meeting in June this year in La Serena in Chile, which is close to the observatories. So this is my life as a observer, I guess, as an observational cosmologist. And I dedicated 90% of my time to this. Okay, so what I'm going to talk today is not my main subject. Anyways, so after 25 years, a standard cosmological model has emerged that can explain all the different detailed cosmological data. So we have data, a lot of cosmological data from CMB, from the galaxy structures, from gravitational waves, lots of different detailed cosmological data. And the model, the standard cosmological model, not to be confused with the standard model of particle physics. So there are two standard models, one in particle physics, one in cosmology. And the standard cosmological model is what we call lambda CDM. What is lambda CDM? Is general relativity plus the other standard model, the standard model of particle physics. And I put this in blue because we understand. And in red, what we don't understand, there's something called the cosmological constant lambda, cold non-baryonic dark matter, and inflation, which is also part of the standard cosmological model. So this talk is going to be about this part here, cold, non-baryonic dark matter. Okay, so far so good. So any questions so far? Curiosities? Okay. Yes. Yes. So we know that the universe is accelerating, the expansion is accelerating. What is causing this acceleration? We call dark energy what is causing the acceleration. And we know that it has to be responsible for, 70% of the energy density of the universe. But we don't know what dark energy is. So there are several models for dark energy. And the simplest possible model is called cosmological constant, where dark energy is given by a cosmological constant. So that's what it is. Okay. Of course, we're maybe if you heard about DESI, there was some results from DESI, these recent results, where there's some very mild indication that the cosmological constant may not be the correct model for dark energy, and that would be incredible. That would be, so some very mild indication that you know the energy density in the cosmological constant is constant during the evolution of the universe. If you find that there's any variation in the density of dark energy, it would not be a cosmological constant. And this is what DESI is testing. And they have results which are, depending how you combine data with supernova, which is another probe, you get 3, 4 sigma. Which is okay, but sorry, the problem. No, it's a probe. It's a probe. So DESI by itself, if you just take so when you do observational cosmology, something funny, no? You have, because you have your experiment and then you take your data, your own data, and then you do your analysis. But in the end, there are other experiments doing other analysis. So in order to take advantage of this huge amount of data, you have to combine them, even if it's not your experiment. So DESI combines their data on BAO with supernova. And when they do that, and also it's more complicated because there are several supernova data. There's Pantheon, Pantheon Plus, there's a supernova from Dark Energy Survey. And then depending on which one you combine, you get different results. And that's life. That's life. You have different data sets, you combine, you get different results. That's life. And the result, the supernova data that gives you the largest deviation from lambda is with the Dark Energy Survey supernova. So which actually, so we are now, I'm Dark Energy Survey, so we're now going back to our data and making a better job combining our supernova with our data and see what we get. We saw this thing coming too. Anyways, yes, more questions? Okay, so dark matter. So what is dark matter? We don't know, right? I guess by now you should know that we don't know. So we have no idea what dark matter is. And in fact, you can think of different mass scales for a dark matter. Well, we think it's a particle or some kind of a, no, black holes are not particles, but some kind of particle-like thing, or maybe even not particle, maybe okay. Anyways, the mass scale of dark matter is absolutely not known. There are, I know, hundreds of candidates that could be the dark matter. Right? All we know is that it's electrically neutral, has to be stable to be around, things like that. So most people here, most people in the community were very much enthusiastic about this candidate for dark matter, which is called a WIMP, which is a weakly interacting massive particle. Why is that? Why is that? Who knows why is that? Because there is a theory called supersymmetry, which is an extension of the standard model that predicts a very good candidates, has good candidates for being WIMPs called neutralinos. They pass all the requirements. They're neutral, they're stable. The lightest neutralino is stable. And Furthermore, they can be produced as thermal relics, meaning that at the early universe, they were in thermal equilibrium. Then they fell out of thermal equilibrium due to the expansion of the universe. And you compute the amount of them that are produced. And it turns out, by chance, that it reproduces what we observe. It's called the WIMP miracle. So many people were so enthusiastic about this. This has to be right. You know, you have this candidate, you have a supersymmetric extension, beautiful supersymmetric extension of the standard model that can explain why the Higgs is not so heavy. Beautiful. No? Well, nature didn't find anything. Didn't find any supersymmetric particle that we're looking for, and didn't find the WIMPs. So people are looking for alternatives. And of course, nowadays there's a big fashion of primordial black holes as dark matter, but and then the masses would be around 10 solar masses. But anyways, this there are other there are other candidates which goes on the extreme opposite of black holes, the very light dark matter candidates, and these are called ultralight dark matter, and they're produced non-thermally. I'll explain why. They are bosonic fields. So this talk will concentrate on ultralight dark matter. So what is ultralight? 10 to the anything that's less than 1 electron volt, I can call ultralight. 1 electron volt. Okay, WIMP is usually 100 GeV, so 10 to the 11 electron volts. I'm talking about 1 electron volt or less. Can be all the way down to 10 to the minus 22 electron volts. Super, super, super light. Okay, and they're so light that these are called wave-like dark matter because their Compton wavelength is 20 angstroms if it's 1 electron volt, which is almost light, or electromagnetic spectrum. And sometimes they're called also fuzzy dark matter because they're not localized. They have this wave-like behavior. Okay, so now I want to talk a little bit because we think this ultralight dark matter are bosonic fields. So I want to talk a little bit how bosonic fields behave in the universe. Okay, and again, if you haven't seen this, and I'm going fast, please stop me. So scalar fields in the universe, I'm sure not sure. Maybe you have seen this, maybe you have not seen this, but you can write an action. You have seen an action for a scalar field, hopefully. So this is a simple, real scalar field coupled to gravity. And the equations of motion can be derived from this action, from extremizing this action. And the metric that we're going to work with is the spatially flat Friedmann-Lemaître-Robertson-Walker metric. So this is the metric. And from this, you get an equation of motion for the field, which is the Klein-Gordon equation that you all know, but modified because of the expansion of the universe. There is this factor, which we call the scale factor, which determines how the universe expands. And they're determined by the Friedmann equation. Okay. So the Klein-Gordon equation is very simple, something like this. This is the term you know, except for this expansion of the universe here, the A factor here, and what's called the Hubble friction here. Okay. And the Hubble parameter is A dot over A, is the rate of expansion of the universe. And for a homogeneous field, which only depends on time, this term drops out. Okay. This term drops out, and you only have this term. And this is the Hubble friction. As simple as that. So that's how a scalar field, a homogeneous scalar field behaves in the universe, okay? And now I can talk about the simplest, in my opinion, model of dark matter. Maybe Farinaldo will not agree with me, but I think it's the simplest. So a free, real scalar field with mass m. What can be simpler than that? I don't know anything simpler than that. So the potential is just 1/2 of m squared phi squared. And then if you plug in the equations of motion is that. If there's no expansion, this is just a simple no expansion, meaning A dot equals 0, a constant, no expansion. This is a simple harmonic oscillator, right? So the field is just oscillating. Now, if you have expansion, a dot different of 0, you have a damped harmonic oscillator. And if the scale factor goes like t to the 2/3, which is what happens when you have um, matter-dominated universes, you can actually solve this equation of motion, and you get that the field oscillates, but also decays with time. See? So this is the expansion factor here, power 3 minus 3/2. And this is what people call in the literature coherent oscillations of this field, but they're damped coherent oscillations. The oscillation rate is the mass of the particle. And if the oscillation rate is much, much less than the expansion rate, the field does not move in a Hubble time. And that's what we mean by a field that's frozen. So if, again, this was a little bit fast, but if the oscillation rate is if the field doesn't really move in one expansion time, then it means that the field is frozen because of Hubble friction. We call this Hubble friction. And the jargon that we use is that the field is frozen. And that happens when at early ages, because age is large earlier, okay? So now when the field starts to oscillate, you can actually take the average of the field in a Hubble time, and it has fast oscillations. So if the mass now, which is the frequency, is much larger than Hubble, one can show, and this is very interesting, that the average energy density of the field, so the energy density of scalar homogeneous scalar field is this, right? 1/2 of phi dot square, so kinetic plus potential term. And you can show that this goes as a to the minus 3 because of this a to the minus 3/2, and you have squares of this. So you can show that the energy density goes like a to the minus 3 of this field. And you can show that the pressure, which is 1/2 of phi dot square minus 1/2 of m square phi square, is 0 on average. So does that ring a bell? What is the field that, what is the energy, what goes like the volume? If you have a bunch of particles in the universe and the volume expands, how does the density, and the particles are not created or annihilated, how does the energy density of a bunch of particles, non-relativistic particles, change with time? The volume goes like 1 over the volume. So the conclusion is, and that's amazing, that a fast oscillating scalar field in the universe behaves as pressureless cold dark matter fluid. Okay? And this is for light scalar fields, because in the beginning they were frozen, and then they start to oscillate, and then they behave as cold dark matter. So the energy density of the scalar field is like a constant, because when at early times, so sorry, this is energy density as a function of the scale factor of the universe. So this is early times, this is late times. At early times, what happens? What happens is that the field is frozen. And if the field is frozen, it behaves as dark energy, as a cosmological constant. It's just a potential energy that's not moving, right? But then after, when the Hubble parameter becomes of the order of the mass of the particle, it starts to oscillate, and then it decreases like a to the minus 3. Okay, so for me this is the simplest model of dark matter. Any questions? Yes. Yes. Previous slide. Yes. Ah, yes. Right. Yes. It will be different, and I don't know exactly how. It will be different, but thanks for asking. So this assumes that the cold dark matter dominates the universe when it starts to oscillate. It will be different, but I don't know exactly. I have to check. It's not difficult to compute. There's no closed solution. I tried. There's no closed solution like that. So I have to do numerical, but that's okay. It's part of. Yeah. Yes. 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 So there's some tautology. Yeah. You're right. You're right. So it's an assumption that the universe is matter dominated when this starts. Yeah. Uh, well, this is not dark energy, right? This is an. Yeah, it behaves as dark energy initially, but not afterwards. So dark energy, sorry, just to interrupt. Dark energy, my definition, is what causes the acceleration of the universe today. This field is not causing the acceleration of the universe today. It behaves as dark energy in the past, but can be very subdominant compared to radiation because, for instance, yeah, and this is related to your question. Radiation dominates here, right? So here it's completely negligible. Yeah. Yes. Yes. But this is when you have usual equality of matter and radiation. So this is much before radiation dominates. It has to behave like dark matter before the equality because we need the structures to grow, and now you get to that. But not too far. It doesn't have to behave like, oops, what did they do? I did something. Yeah. So it doesn't have to behave as dark matter here, for instance, at early enough times. Yeah, because radiation dominates everything. But now, yeah, I want to, since you asked this, there's another thing I should tell you because that's interesting. If I assumed a potential that's phi square. Suppose it's not phi square. Suppose it's phi to the power n. You can show that it doesn't go like a to the minus 3. It depends on the power of the potential, and that's easy to show. And in fact, if the potential is phi to the 4, it goes like radiation, it goes like a to the minus 4. And if it's larger than phi to the 4, it goes faster. It decreases faster than radiation. You can show that. I can show that. Even I can show that. And that's very interesting. You know why? Because there's something called early dark energy, which was it's a model where you have an early component of dark energy that has to disappear, and that's a way to disappear with dark energy very quickly, is to have a potential that's larger than phi to the 4. And these are models of early dark energy, but I'm not going to talk about this. I have worked on that too, but I'm not going to talk about this today. So thanks for the questions. So let me talk now about this misalignment mechanism. Okay, I'm doing okay. So again, when Hubble is much larger than the mass, the field is frozen at some value phi naught. And it could be that this value of the field that's frozen is not at the minimum of the potential. And that's what is called misalignment. This is it. The misalignment is the fact, is the possibility that the field value initially is not at the minimum of the potential. So again, it's some dark energy because it's frozen, but not dominant, okay? It's early on, so radiation is domination. Okay, so when Hubble becomes of the order m, this field here will start to oscillate. And then it behave like cold dark matter. And they start to oscillate, the field starts to oscillate when Hubble becomes the mass. And I'm going to come back to this. It's not difficult to compute when. Now, the thing is that the initial energy density of the dark matter is this energy density here. It's exactly 1/2 m squared phi naught square, the initial value, right? That's the energy density that is contained in this field, and then it starts to oscillate, and then it dilutes like cold dark matter. So today you can compute what is the density of this field if initially was this, Then there's just a dilution factor that you can compute, which goes like the volume, or if you want, the temperature to the cubed, to the third power, because the temperature is inversely proportional to the scale factor A. So that's why I think this is the easiest model for dark matter, simplest model, because you can easily compute what is the contribution of this misalignment field to the dark matter density. So this omega dark matter, which is the ratio of rho dark matter divided by rho critical. So rho critical is basically H naught square and Planck square. If, if you don't know, yeah, okay. I guess you have to trust me, but this is just Friedman's equation. And then the rho dark matter is what I wrote there today, is this. And you can compute what is the time when the field starts to oscillate, is also given by basically Friedman's equation. This is Friedman's equation because, okay, I can show you that. Not easy, difficult. This is just approximations, right? Just to get a feeling of the numbers. So so this starts to oscillate when Hubble equals mass, and then the temperature of oscillation is the square root of the mass of the particle times the Planck mass. So you can plug in the numbers, and if I didn't make any mistake, which is very possible I did, omega dark matter is of the order of the mass and divided by 10 to the minus 14 electron volts to the power of half, and phi naught, which is the initial value of the field, divided by Planck mass squared. So that already hints that in order to have omega dark matter of order 1, you need a very light mass, ultralight. Very simple calculation. And I hope I didn't make any mistakes. It's possible I made a mistake, but okay. Questions? So it just comes from this, okay? Actually, it just comes from this very simple thing that the energy density today is just the initial energy density, which is given by is set by the value of the displaced field and the dilution factor. Now, isn't this the simplest model for dark matter? For me, this is the simplest model, and this is non-thermal. Okay, why this is non-thermal? Because these particles were never in thermal equilibrium. They're very weakly very weakly interacting. And then I always get this question, and I ask you this question. Look, this mass is very small, 10 to the minus 14 electron volts. How come it behaves like non-relativistic matter? I always get this question. Think about it. I gave the answer already, but you would think that this very light particle would, 10 to the minus 14 electron volts. You know what's the temperature today of the universe? What's the temperature today of the universe? 3 Kelvin, right? In electron volts. 10 to the minus 4. This is way lighter than the 10 to the minus 4. Why is not relativistic? Think about it. Okay, so now I'm going to talk about ultralight. So this was just to motivate the idea that in this very simple models of misalignment, you basically require a very light dark matter particle, a 10 to the minus 14, something like that. Huh? Oh, it's not moving at the speed of light. That's what I mean. Yeah. Why not, right? Why? Because these are coherent. So this comes from coherent oscillations. So these particles are like Bose condensates, and they travel very slowly. They're absolutely non-relativistic. Okay, so now I'm going to talk about the most well-studied model for ultralight dark matter. And those are called axion models. So first of all, ultralight, or even light, scalar particles are not natural. You know what natural means? Naturalness? It's just the fact that when you compute, for instance, quantum corrections to this potential, if it couples to anything, you get things that diverge quadratically. So that's why scalar particles are not naturally light. But here we have an ultralight particle. How come? Well, the mass must be protected somehow. And the way to protect a mass is using a symmetry. And this is exactly what happens in the case of the axion. So an axion, or more generally what's called axion-like particles, you have a complex scalar field. So it's a bit more complicated than the simplest model. It's a complex scalar field, which I can write as a radial part and an angular part, which is charged under U1 global symmetry. So you can write a Lagrangian that has a U1 global symmetry. And this U1 global symmetry, if you look in the literature, is called Peccei-Quinn symmetry because of Roberto Peccei and Helen Quinn, who actually postulated this model in the context of to solve the strong CP problem, which maybe you heard, maybe you have not heard, but I can talk later maybe. Okay. So you have a very simple quartic, sorry, there's a square here missing. It's a quartic potential, you have symmetry breaking, and this potential here is this, as you know, this Mexican hat potential, and here in the bottom of the Mexican hat, you have the angular direction, which doesn't cost any energy to go around because there's no bumps going around. So the angular variable has a shift symmetry, and is massless. So this is because there's no potential for this angular variable. And this is the axion field. This is basically the axion field, A here, which is just this angular variable is related to the axion field divided by the vacuum expectation value of the scalar field. So at this point, the axion is massless, but we know that there are some contributions that break this global U1 symmetry explicitly, and this is typically by non-perturbative effects, and this generates a potential for the axion. So the axion, in principle, is massless. Why is it massless? In principle, right? So let me go back. I think I forgot to mention one important word here. It's a massless Goldstone boson. So who have heard of something called the Goldstone theorem? You have. You have. Good. So Goldstone theorem says exactly that. If you have a broken global symmetry, exact global symmetry that is broken, you have a massless boson associated with it. And this is the Goldstone boson. And the axion is the Goldstone boson of the symmetry break. Okay. But the global symmetry is not exact, and you can generate a periodic potential for the axion field A here. And if you expand this cosine, you get the first term is a mass term, and the mass term is this scale here, which is an infrared scale, where these non-perturbative effects become relevant, divided by this F, which is the scale of the symmetry breaking, which can be very large. So axions can be naturally light, naturally because their mass are protected by the U1 symmetry that's spontaneously broken and explicitly broken here. So the mass is naturally protected, and if you plug numbers like a 1 GeV for lambda and 10 to the 15 GeV, you easily get 10 to the minus 6 electron volts for the axion. So the QCD axion, which I'm not talking about, also acquires mass due to non-zero quark masses that also violate the Peccei-Quinn symmetry, if you ever study this Peccei-Quinn symmetry. Okay, so axions can be the dark matter through the misalignment mechanism, and there's many experiments that looks for axions. And I stole this slide from a presentation, but here is you cannot see because the resolution is not very good, but here is the mass, and here is this scale F of symmetry breaking. And these lines that I highlighted are because of the misalignment mechanism, but okay. So axions are one of the favorite models for ultralight dark matter. Okay. Now, axions are not free of problems. There's something called axion quality problem. And the axion quality problem is the following. In general, you can have higher dimensional operators, which can be suppressed by the Planck mass, that also break this U1 global symmetry explicitly. And what you want is that you don't want these operators to spoil the properties of the axion potential, at least the QCD axion potential. So I'm going to speed up a little bit because otherwise I'm not going to the end. But in order to avoid this type of dangerous higher dimensional operators, you need some way to avoid them, at least to some order n. And in fact, you can show that you need n larger than 12 in order to not have what's called the equality problem. And why is n larger than 12? This is not fully understood. There are several works about that. Okay. So finally, I get to the topic of this talk, okay, which is another candidate for ultralight dark matter. And these are dilatons. So I'm going to talk a little bit about what dilatons are. So dilatons are, remember, I want them to be ultralight. So I want a particle that has a mass that's protected by a symmetry. The axion was protected by this global U1 Peccei-Quinn symmetry. And the axion was a Nambu-Goldstone boson of the breaking of this U1 symmetry, global U1 symmetry. The dilaton is also a Nambu-Goldstone boson. Of what symmetry? Of something called conformal symmetry or scale symmetry in some cases. So we have an approximate scale invariance, and the mass of this dilaton. So the dilaton is the Nambu-Goldstone boson associated with the breaking of the scale invariance, and its mass is protected by this approximate scale invariance. But if you talk to other people, they have different definitions of dilatons. So if you talk to people doing scalar tensor theories, they say, oh, there's a dilaton here because I can do a Weyl transformation, go to the Einstein frame. So I just put in this because there are other people means different things for dilatons. In string theory, there are dilatons in string theory. Reynolds-Sundrum models, there's radium, which is a kind of a dilaton. And there are extensions where I have Higgs dilaton models, axion dilaton models, etc. But I'm going to concentrate on this definition that the dilaton is a pseudo-Nambu-Goldstone boson that arises because of the scale invariance breaking. And dilatons can lead to very interesting phenomenology. It can lead to fifth force, so another force in addition to gravity. It can lead, if light enough, of course, to be mediating long-range interactions. It can lead to a violation of the equivalence principle, if not universally coupled to the trace of the energy momentum tensor. And it can lead to inflation, dark energy, dark matter, etc. So I'm going to be interested in the dilaton as dark matter in this case. And this is an old story. I just put this is hard to see, but it's from the 70s, one of the first papers looking for dilatons as possible fifth force kind of thing. And again, I apologize for the resolution, but this is a plot showing the bounds on fifth forces, so deviations of the Newtonian force caused by dilaton exchange. And the strongest bound on the dilaton mass actually comes from cosmology. That's why I spent a lot of my time in cosmology. It's from something called the Lyman alpha absorption lines from quasars. And this is the strongest bound that there is. So the mass of the dilaton has to be larger than 10 to the minus, not very strong, no? 10 to the minus 20 electron volts. And just maybe I will skip this, but if you want to learn more about dilatons, I really recommend these lectures by Sidney Coleman. Have you heard of Sidney Coleman? So he has these fantastic letters called Dilatations in the 70s, and I recommend to take a look to learn more about scale symmetry, etc. And also the dilaton coupling, yes. So you can show that the dilaton phi here couples to the trace of the energy momentum tensor. And this is very interesting because the trace of the energy momentum tensor is a signature of scale violation, and it's proportional to masses and beta functions. And the fact that it's proportional to masses here, it makes the dilaton couplings to be very similar to the Higgs couplings. And when the Higgs was found, some papers were saying, "Oh, well, is it really a Higgs or is it a dilaton?" So There are papers you can Google it. Higgs imposter. This was the name of this thing. So this is just a curiosity. So in principle, one can take a phenomenological approach where the mass of the dilaton is a free parameter, and the coupling to standard model is given by this trace of the energy momentum tensor of the standard model. So you can do something very phenomenological, pure phenomenological approach. This model has only two free parameters, the mass and the scale f. That's all. And there are many papers that have taken this phenomenological approach to study dilaton. That's not what we're going to do. Okay. So in this work, what we want to do is to investigate if the dilaton can be ultralight dark matter from a misalignment mechanism in a realistic model. That's the goal of this very actually this work is very short. I'm making a long story here, but the actual paper is 2 pages or 3 pages. And here just make a comparison between axions and dilatons. But okay. So now I'm going to talk about the dilaton mass in some realistic models. And there are two important papers in 2013 that discuss the possibility of naturally light dilatons. And one of the authors of the second paper, Jay Hubish, is one of my collaborators on this paper. So there's a conundrum about scale invariance. So scale invariance allows a potential for a scalar field, which is purely lambda phi to the fourth. However, if lambda is larger than 0, the minimum of this potential is a 0. And there is no breaking of scale invariance. If lambda is less than 0, the potential is unstable, is unbounded from below. So the only possibility to have, in principle, scale symmetry breaking is to have a degenerate potential, flat direction. And this is a conundrum. So in order to actually have a model where you can have symmetry breaking, you actually need a small explicit breaking of scale invariance. Otherwise, it would be a flat direction. And this small explicit breaking is related to the mass of the dilaton, as I will show. So the idea is to add, in 4 dimensions, a near marginal operator in the CFT with dimensions 4 minus epsilon that condenses and has a non-zero vacuum expectation value. And then you can have different different models for symmetry breaking, but I will skip this and I show something better. So a useful model to have in mind, for instance, is this one, which is a phi to the fourth potential, which is modified by a higher dimensional operator, which has a very small anomalous dimensions here, epsilon. And and phi star is when the potential is 0, and the minimum is not very is very close to phi star. Actually, you can compute this analytically, and the mass is proportional to this parameter m squared here, and the proportionality is epsilon, which is a small parameter. This I just plot this potential for 2 values of epsilon. However, if you want to have very light dilatons, they have to be associated with a conformal sector, which is not related to the standard model. So it has nothing to do with the standard model. Otherwise, you cannot have very light dilatons. And this is called the dark conformal sector. And so we assume that the mass of the dilaton is this small epsilon times the vacuum expectation value, or the scale of conformal symmetry breaking, if you want. And from an effective field theory of the dilaton field, this is valid for energy scales smaller than 4 pi times f. All right, I think I will skip this. And I talk about this quality problem of an ultralight. I have 5 minutes to finish. Quality problem of ultralight dilaton. So it's useful to recast this generic dilaton potential, which is just lambda phi to the fourth, with something that has explicit symmetry breaking. So you imagine that this coupling constant lambda actually is a function of the field phi. It's like the coupling is running. And you know that running, maybe you don't know, but if your coupling is running, that introduces a scale, and you break conformal, you break scale symmetry explicitly. So that's why I call this an explicit breaking of the symmetry. And you can formally define a beta function, which is how this coupling constant varies with the logarithm of this field phi. And there are many things you can show, but you can show that the minimum occurs at a certain value of the beta function when beta function is minus 4 lambda star. And you generate an infrared scale f. And expanding the field phi around the vacuum expectation value, and these are the excitations, you get the mass of the excitations to be this beta star, the fixed value, the fixed point value of the beta function times f squared. And the dilaton can be light if you have a very small beta function. What is the problem with this? The problem with this is that if this coupling is running, you can show that the run of the coupling between the ultraviolet scale and the infrared scale f, where the symmetry breaking occurs, is exponential. If I assume that beta is an epsilon parameter here times some function which is order 1. And this epsilon parameter, which is small, is related to the mass of the dilaton. So basically what you have is that the mass square of the dilaton divided by the infrared scale, or the scale of symmetry breaking, is basically the coupling constant in the UV, which is order 1, divided by this log of lambda UV divided by the mass of the dilaton. Why is this relation important? Because you cannot have lambda UV to be larger than the Planck mass. So, and this is the quality problem. So the quality problem requires that the cutoff, the ultraviolet scale, cannot be larger than m Planck. So for the mass of the field between 10 to the minus 22 and 1 electron volt, if you plug this here and lambda of order 1, because it's a logarithmic dependence, you see that m square over f square, which is actually the small value epsilon, can be at most between 0.01 and 0.1. So this is important, okay? It means that you cannot have a large separation between the mass of the dilaton and the vacuum expectation value, or the scale where symmetry, the scale symmetry is broken. And the same result can be derived, and we do that in the paper. We do that in the paper in the context of a 5-dimensional Randall syndrome model, where the dilaton is actually identified as the radium. Now, this is a very important. This is the thing you have to remember now. Okay, please remember this. If you want the UV scale to be smaller than the Planck mass, this epsilon parameter has to be between 0.01 and 0.1. Remember this? Don't forget. Okay, good. And now the last part of the talk. What are the consequences for ultralight dilaton dark matter? As I mentioned before, the misalignment mechanism predicts the dark matter today in terms of the initial value of the displaced field. Now, if we assume that this oscillations starts at 1 kilo electron volt, so this is way before the equality of matter radiation, and we assume that the initial value of the field has to be smaller than 4 pi f, and this is because we're using an effective field theory for the dilaton, and also requiring that as usual, that the density in dark matter equals the density of radiation at matter radiation inequality. So basically, that this at matter radiation equality, this T equality here, you have this relation. And using that F is m phi divided by square root of epsilon, so this relation here, plugging all the numbers, and this is what comes out if you want an ultralight dilaton dark matter, that this factor epsilon here, which is related to the smallness of the dilaton field. If you plug all the numbers, you get that epsilon has to be smaller than 10 to the minus 8 in order to have a good quantity of dark matter. So that's all this paper that we did, all we did in this paper was to point out that this is inconsistent with this. So if you want a dilaton model where the cutoff, the ultraviolet scale is smaller than mass Planck mass, this epsilon has to be between 0.01 and 0.1. And if you want the dilaton to be ultralight dark matter, you need something that's smaller than 10 to minus 8. It's not possible. So dilaton, this is the conclusion, cannot be ultralight dark matter through the misalignment mechanism without a huge quality problem. So did we kill this nice model? Are there ways out? We don't know yet, okay? But I would argue now that if you want an ultralight dark matter, a dilaton model would be not reasonable, would be not be natural. And this is the conclusion of the paper. And it's 5 o'clock. Thank you. So this was the title of the talk, if you remember. Let's see if you remember this.